So let's look at the following example that will deal with Gauss's law. So let's begin. A charge positive Q is distributed uniformly and continuously throughout a non-conducting solid sphere with radius r0. Calculate the electric field at points outside the solid sphere in part A and in part B at points inside the solid sphere. So, let's begin by looking at our diagram of the solid sphere with a radius r0. Now notice, because we're dealing with a non-conducting solid sphere, that basically means all the charge will be distributed evenly and continuously throughout the entire solid sphere as shown. Now we basically want to apply Gauss's law to solve this example. Now Gauss's law states that the net electric flux is equal to the closed integral of the dot product EdA, which is equal to the charge enclosed within our region divided by epsilon naught, the permittivity of free space constant. Now let's begin with part A. Calculate the electric field at points outside the solid sphere. So to essentially apply this law, we have to choose a certain region whose surface contains the points that we are studying. So we choose a region whose surface contains the points found outside the solid sphere. Now we can choose any region whatsoever, but we're going to choose a spherical region so that there's symmetry. And symmetry will allow us to simplify some things, as we'll see in just a moment. So we choose a sphere whose points lie on the green region shown by the following outline, green outline. Now, the radius of our outer sphere, r, is larger than the radius of our solid sphere given by r0. So r is greater than r0. So we essentially want to ask ourselves, what exactly is the electric field at all the points found on the following green outline? Now, by the symmetry of the sphere, because electric field depends on the distance, and the distance on this region is the same, it's the distance given by r, that means the magnitude of our electric field on the surface of the chosen sphere is exactly the same. The magnitude is the same, and the direction is always perpendicular with respect to the green surface. So since the electric field is perpendicular to the surface, and because this dA is always perpendicular to the surface, that implies that our electric field is parallel to dA. And because they point in the same direction, that implies that our angle between these two vectors is 0. And this will become important in just a moment. So now we are ready to apply Gauss's law. So the net electric flux is equal to the closed integral of dot product EdA. Now by definition, dot product is equal to, so we have dot product of two vectors, and that is equal to the product of the magnitude of the two vectors multiplied by the cosine of the angle between them. Now, the cosine of the angle between them is 0, and cosine of 0 is 1, so this becomes 1. And notice our electric field E is a constant at all points around on the following green outline. So that means this is a constant, and we can bring that outside of our integral, and we get the following result. Now we actually evaluate our closed integral, and we get this is equal to E multiplied by A, the surface area. Now, because this is a solid sphere, that means that the surface area is equal to 4 pi r squared. So E multiplied by 4 pi r squared is equal to this ratio by Gauss's law. So this is equal to the total charge enclosed given by Q divided by epsilon naught. So now we take this, rearrange it, and solve for our E. And we see that the electric field at all the points outside this solid sphere is equal to the charge Q divided by 4 pi epsilon naught multiplied by r squared. So, what exactly is the relevance of this equation? This equation is the same equation for our Coulomb's law for electric fields produced by static point charges. So that basically means if we're examining points outside this solid sphere, it's as if all the charge exists as a point charge in the middle of our sphere. Now, let's move on to part B. Calculate the electric field at points inside the solid sphere. So we have to actually follow the same exact procedure, except now we choose a sphere found inside our solid sphere. So we choose the following green region. And let's suppose now the radius of this small green region is given by r, and now r is smaller than r naught. Now, before we actually apply Gauss's law, we have to define something called the charge density. Now, the charge density given by rho is equal to the charge divided by the volume. And because our charge is distributed uniformly and continuously, this charge density is constant throughout the entire region. So that means this is a constant. This ratio of charge divided by volume is constant. Now, when we apply this equation, we have to know what the charge is of this chosen region with radius r. So how much charge Q is in this green sphere. So we know our charge density, our rho, is constant. So rho is equal to, so let's begin with this full solid sphere. So we have Q total, which is simply this Q divided by the volume of that entire region. So 4/3 pi r naught to the third power. And this is equal to the charge enclosed in this region. Let's say that's Q enclosed divided by 4 pi r, because this is the radius of the smaller sphere to the third power. And this ratio is equal to this ratio because our density is constant. Our charge density is constant. Now, we could solve this equation and solve for our Q enclosed. We see that the Q enclosed is equal to the Q total multiplied by this ratio. And notice the 4/3 and the pi will cancel, and we're left with the following result. We'll need to use this in just a moment. So, now we apply Gauss's law, and we follow these same steps as before, and we get to this result. So our electric flux is equal to E multiplied by 4 pi r squared, and this is equal to the charge enclosed in this region divided by epsilon naught. So now we take this charge enclosed and replace it with this, because our charge enclosed is equal to the total charge multiplied by r third divided by r naught to the third power. So that's exactly what we do, and we get this result. So now we see that the electric field multiplied by 4 pi r to the second power is equal to this whole fraction. And now we solve for our electric field, and we see that the electric field is equal to the total charge Q given initially multiplied by R divided by 4 pi epsilon naught multiplied by R naught to the third power. Notice R naught is a constant. It was chosen to be a constant because it was fixed. So this entire fraction is a constant, and we see that the electric field depends only on R. In fact, the electric field increases linearly with respect to R, as shown by the following equation.